Hi, and welcome to Lecture 5 for Math 1B03. In today's lecture, we're going to be looking at the matrix equation AX equals B. And the material of today's lecture is based upon section 1.4. Now, just a quick recap of what we were doing last lecture. In the last lecture, we looked at linear combinations of vectors. So just remember what that means is we take any collection of p vectors in Rn, and we take C1 through Cp to be real numbers, and we do a linear combination of those vectors, and we can make new vectors from that. In today's lecture, what we're going to be looking at is what we call the matrix equation of AX equals B. And we'll see the linear combination notion come up a number of times in today's lecture. So the point of the main takeaway from today's lecture is we're building a new framework or a new point of view of looking at a system of linear equations. So basically what we'll be seeing is that we can use a matrix A, which stores some of the information about our system of equations, and manipulate it to say something about the solution set that we're interested in. So let's jump in and first talk about what we mean by this expression right here, A times X. Okay, so let A be an M by N matrix, and just to make this clear, what this means is we have M rows and N, here, I'll make this a little neater here for you, M rows and N columns. So we have an M by N matrix, and here are the columns, A1 through AN, so each of these represent a column, so you want to think of each of them as vectors containing M numbers. If we take a vector in Rn, then the product of A and X, denoted A times X, is the linear combinations of the columns of A using the corresponding entries of X's weights. Now, this may seem a little complicated at first glance, so let me just explain a little bit more clearly. So we're looking at A times X. So you want to think of your matrix A is corresponding to a bunch of columns. We have N columns. And so each of the AIs represent a vector with M entries, and we're multiplying it by a vector x1 through xn. And what this means is we're taking x1 times the first column. We're taking x2 times the second column. And we do this all the way through. We're basically scaling each column by the corresponding weight and then adding all of the entries up. And so we're getting a new column, a new vector. Okay, so let's make this a little bit more clear through an example. Here I have a matrix A. Okay, and so just so you can keep track, it has 3 columns, and we can write each of the columns as vectors. So the first column is 1, 2. The second column is -2, 3, and the third column is the vector 1, -2. Now let's say I have a particular vector that I'm looking at. Let's say I'm looking at the vector 1, 6, -1. Then what do I mean by writing A times X? Well, that means I'm taking my matrix 1, -2, 1, 2, 3, -2, and I want to multiply it by my vector. Okay, and according to the formula on the previous page, this means take 1 times the first column, so scale the first column by 1, scale the second column by 6, and scale the last column by -1, and then add up all the corresponding entries. So at the end, we would get 12 and 22. Just to make sure you know where this is coming from, we have 1 times 1, which is 1, plus 6 times -2 is -12. Oh, this should be -12, and plus -1 times 1. So the 1's cancel, and I'm left with -12. And in the bottom spot, I have 1 times 2, which is 2, plus 6 times 3 is 18, and then plus 2 more, so I have 22 in the second spot. So let's carry this a little bit further and let's try to connect things to systems of linear equations, which is something that we're interested in. So here on the left-hand side, here, right over on this part right here, hopefully you can see my cursor, this is a system of linear equations one might be interested in. And we saw from lecture 2 and 3 that we can associate to such a system of linear equations an augmented matrix, right? So the kind of the key stuff is the coefficients and what the system is equal to, right? So we have 4, 5, 6, 7, 8, 9. And we're going to keep track that it's the augmented matrix, right? So we have our augmented matrix for our system of linear equations. And then last time, in last lecture, I'll put this right here. From our last lecture, we noticed that, well, if you're interested in solving the system of linear equation, you can rewrite it as a vector equation, right? So we can rewrite this as we're trying to solve x1 times the first column plus x2 times the second column plus x3 times the last column. And we want this vector equation to be equal to 0, minus 3, and 6. And now from the previous definition on the that I just gave at the beginning, that this expression right here, so here let me put this right here, from the first definition from our lecture today, is that this is actually the same thing as the system of equations 1, 4, 7, 2, 5, 8, or I should say matrix multiplication by a vector 0, minus 3, 6. So the takeaway here is that we have a system of equations and you can rewrite it in the form of ax equals to b. So one way to think about solving system of linear equations is that you're trying to solve equations of this particular form. So to summarize here, the following theorem here kind of summarizes everything that we just talked about, is that really there are three ways to view a system of linear equations. Okay, so we can have, and it's capitalized in the statement here, so let A be an m by m matrix with columns a1 through an in Rm and some vector b. Then the equation ax equals b with x going from x1 to xn has a solution set as this vector equation, which has the same solution set as the system of linear equations with this augmented matrix. So we have three different viewpoints of looking at a system of linear equations, and we want to be able to flip quite easily between these different perspectives as we move through the course. We will take a short break here to get ready for the next part of the video, where we're going to talk about how to look at the matrix to talk about existence of solutions.